Hi, this is Chris Goss at Linear Technology. At this point, you have completed your initial design, and now you would like to look at the performance of the switching converter. And so we review this by looking at the stability and transient response. We are now on the Loop Comp and Load Transient tab. The Loop Comp and Load Transient tab will import from the power stage design the information on the left-hand side, the design specifications, the inductor value, the output capacitors. It will also import the feedback resistor divider and the compensation components that you selected on the power stage portion of the design. An important value to look at here is the desired bandwidth. The desired bandwidth, as a rule of thumb, is selected to be between 1/5 to 1/15 of the switching frequency. A conservative design will select 1/15 of the switching frequency. An aggressive design will select 1/5 of the switching frequency for the desired bandwidth. Let's look at the results of this bandwidth. So we have here in the center now the loop gain graph, which shows us the gain versus frequency and the phase result versus frequency. So we can see that the resultant loop gain here is 63 degrees, and that's written down on the bottom left. And we have the cursor also right over the crossover, which also shows us to be 63 degrees. The phase margin is 73 degrees, which is very stable. The phase margin you would want, as a rule of thumb, to be greater than 30 degrees. This will make the design unconditionally stable. So we have a design that is stable right off the bat. We're pretty lucky. So the next thing that we want to look at is the transient response. And the amplitude of this transient response is going to be directly proportional to the output impedance. I have switched over to the output impedance tab in the center to look at what the output impedance is. My output impedance is around 6 milliohms. And you can see that on the bottom left. You can see what the impedance is where my cursor is showing. Now the transient response is going to be directly proportional to the 6 milliohms of impedance. In this case, I have a load step that is pre-selected to be a 4 amp load step. It is going from 6 amps to 10 amps. And so a 4 amp load step with 6 milliohms will yield this result that's about close to 40 millivolts. Is that 40 millivolts sufficient of deviation? You have to tell me. I don't know the spec that you're designing to. You have to consider that that is within your regulation window. So your regulation window will include the accuracy of the reference, the DC set point accuracy, and the transient response. So this is the hardest part, is making sure that your regulation window is within that. So let's say that this is not enough, that I need my transient response to be less than 20 millivolts. What do? The only choice that you have is to increase the number of output capacitors to reduce the ESR, which reduces the impedance shown here. So I will increase the number of bulk capacitors from 1 to 5, and let's see the result. The graph is rescaled, be careful, and we can see that the transient now is less than 20 millivolts, so it's below our target. This is good. Are we done? Well, no, because now that we've changed the output capacitors, we need to also go back and look at the loop gain to make sure that the loop gain is satisfactory. So I'm going to go to the loop gain tab again and look at the result. So you can see by adding the 4 output capacitors, the bandwidth has now come down significantly. It's come down from 60 kilohertz to about 20 kilohertz. And looking at the plot numbers, it says that it's gone down to 17.7 kilohertz. The phase margin has reduced a couple degrees down to 69 degrees. This is still very stable design. We're lucky we don't have to change any of the components. Let's say, though, that we want to get the bandwidth back up to the 60 kilohertz number that was our target. What would we change? The easiest thing to change is the RTH value to increase that. So I'll change that to 20 kilohertz. And you can see that increased the bandwidth, and you can see also how it changed the transient response. And now there was a little kind of damped ring there, but that damped ring is gone now on the transient response. So this design looks good. There is no further changes that I would make to this design. This concludes the load transient and loop compensation section of the design for this video on LTpowerCAD. Thank you for your time.